Hello, my name is Dana Gifford, and this session is about factorial experimental design and blocking. So what is factorial experimental design? A factorial experimental design is generally used to investigate the effect of two or more explanatory variables on a response variable of interest. Some scientific questions you might ask with a factorial design include things like, what is the effect of diet and exercise on blood pressure? Do soil type, irrigation, and fertilization affect the growth rate of wheat? And considering current events, you'll hopefully heard about the promising news about the COVID-19 mRNA vaccine. One question we could ask is whether vaccination has different efficacy in males and females, given that we know COVID-19 has different effects in males and females already. Factorial designs tend to be applicable to certain types of experimental data. Although what I'm going to present is by no means hard and fast rules, this is a general guide. Typically, the explanatory variables in a factorial design are categorical. That is to say, they have discrete categories or labels. We call this type of variable a factor, which is a concept you might have encountered already in your practice with R. An example of a factor is something as simple as types of fruit, for example. A factor can have any number of levels. When you're considering fruit, for example, and these levels can be apple, banana, orange, strawberry, etc. Now, in a factorial design, the response variable, by contrast, is often numeric, and all of the examples we'll consider today will be of this form. It's important to note, however, though, that explanatory variables don't necessarily have to be categorical. They can be numeric, but binned into categories. And response variables can also be other types of data, but we'll cover this more in a later session. Here are some common terms you might encounter when considering factorial experimental design. The first is two-way factorial design. What do we mean by this? When we say two-way factorial, what we refer to is a model that involves two factors. And each of these two factors can take any number of levels. And here I've given a few examples of factors that have more than two levels. It's important to consider that any factor, for any factorial design, you need not consider all possible levels of these factors, but could be considering only a subset if this is appropriate for your specific experiment. So we have two-way designs, but we're not constrained to only looking at two factors. We can also have, by extension, n-way factorial, which is a design with n factors. We could consider, say, for example, the effect of sex, education level, and ethnic background on some response variable of interest, like the response of the immune system to COVID-19, for example. Now, the term fully factorial or cross design is another one that you may come across. And this simply means that every possible combination of the n factor levels under consideration is represented in the data. If I'm interested in education level and ethnic background, for example, I will have data points from all ethnic backgrounds who have achieved each level of education. A fractional factorial design is, by contrast, a design where not all possible combinations of the factor levels are represented. This may arise simply as a natural consequence of the way the data are collected, as is common in many ecological studies where controlled experiments are not always possible. But a fractional factorial design can also be intentional and can be useful in cases where a carefully chosen subset of the factor combinations is represented in the data. This compromise might be made due to, for example, say, cost of running the experiment, but any approach requires careful and thoughtful design to avoid incorrect inference. Some important considerations you need to take when deciding whether a factorial design is right for the type of scientific question you want to ask are, first, the factor levels should be non-ambiguous. Any one experimental unit should only fit into one level of each factor. For example, if my factor is fruit, any individual unit cannot be both an apple and a banana, say. It just can't. Second, factorial designs are most efficient and the statistical approach is most accurate when group sizes are equal. So, for example, there should be the same number of apples as bananas under consideration, same number of males and females, and importantly, the same number of males who ate bananas as females who ate apples and vice versa. Having group sizes that are unequal can lead to inference errors, especially when the two factors can be confounded. And our modern statistical software can cope with unequal group sizes to an extent, in that it will happily produce you test statistics and p-values, but it may potentially warn of unbalanced effects. And it's up to you as the researcher to decide whether these are problematic or not. Now, finally, with factorial designs, it's often tempting to include too many factors in your design all at one time. Unless there are some clear hypotheses involved, having more than 3 factors can be hard to interpret. It's always important to consider what your scientific objective is, and if this can be achieved with a simpler experimental design. Software can, of course, cope with many more factors than 3, but here the limitation becomes what inference you as the researcher can make, what story you can construct with a model having so many factors. Let's look now at a hypothetical example. So as we've recently learned, Pfizer has come up with what looks like a promising mRNA-based vaccine against COVID-19, which so far appears to be about 90% effective. However, the efficacy of this vaccine still needs to be demonstrated in the wider population. So there will be still some months before we know for certain how well it's going to work. One of the ongoing concerns about COVID-19 is that the symptoms seem to be worse in males than females. It's worth asking then whether the vaccine will be more effective in males and females, and really how effective it will be overall. Let's look at some possible experimental designs we could use to address these questions. Here I sketched out diagrams of what 3 experimental designs could look like. One design we could use is to investigate only a single factor, vaccination status. And here we randomly assign volunteers to either the vaccinated or control groups without regard to their sex. Right away, we see this as problematic because it only lets us address one of our 2 questions. We can ask whether the vaccine is effective overall, but we can't ask whether the efficacy differs in males and females because we could potentially have different numbers of individuals in each group, and we're not designing an experiment to look at this explicitly. A second design we can use is to do 2 separate experiments, looking at one factor at a time, a so-called OFAT experiment. In experiment A, we test the effect of vaccine in males, and experiment B, we test the effect of the vaccine in females. A third design we could use is to do a single experiment, but within that experiment, assign equal numbers of males and females to the vaccinated group and equal numbers of males and females to the control group. Given that only these 2 sorts of designs let us ask questions about both the effect of sex and the effect of vaccination at the same time, we will next consider how these 2 designs stack up against each other. So, at first glance, it might appear that these 2 designs are effectively the same. I have vaccine groups, I have control groups, and I have individuals of the 2 sexes apportioned to these different groups. So what's the difference, you might ask? You might be thinking actually that the OFAT design is nice and simple. I change only one aspect at a time, and surely that accounts for something. The objective here, though, is to demonstrate that the benefits of a factorial design usually outweigh the simplicity of an OFAT design. And if we analyze the factorial design correctly, then we can get actually more information from the factorial design with less resources than an OFAT design. You might have noticed in my representation that there are actually twice as many volunteers represented in the OFAT design than the factorial design. And this isn't just an accident. In fact, this is because to achieve the same precision, the OFAT design actually requires twice as many experimental units. However, efficiency aside, there are also crucial differences in the inferences we can make using these 2 different types of designs. For one thing, doing 2 separate experiments A and B allows the possibility of introducing extra noise. For example, what if experiment A received a faulty batch of vaccine that had been left out of cold storage too long? Or if the nurse doing the injections were having a bad day? Or any number of possible things that we can't control for or even necessarily know about. Crucially, though, one of our scientific questions involved comparing the efficacy of the vaccine in males and females. This type of question involves looking at the interaction between our 2 factors, vaccination and sex. Considering interaction effects is not possible with an OFAT design due to the potential that the effect of sex is obscured, or as we say, confounded by these unknowable differences going on between experiments A and B. These issues, both in terms of the efficiency of the resources, then the amount of resources needed, and the ability to look at interaction effects can be ameliorated with a well-designed factorial experiment. However, that's not to say that there aren't some disadvantages to a factorial design. Particularly, they can be incredibly complex to design if we're considering maybe more factors and more levels than we're considering here. Furthermore, the parametric statistical methods we have to analyze these types of design are not especially robust against unequal group sizes. Say, for example, for some reason we had more male volunteers than female volunteers and couldn't have equal numbers of each. This used to be more of an issue when we had to calculate test statistics by hand, but the ability to estimate effect sizes might be different, and your software will warn you of unbalanced effect sizes when analyzing data with unequal group sizes. By and large, however, the benefits of a factorial design usually outweigh those of an OFAT design. And in general, you should have, if you are going to use an OFAT design, you should have a very specific and well-justified reason for using that approach, not just simply that it's easier to instruct.